My name is Boris Voloskov. I'm from Moscow, from Skolkovo Institute of Science and Technology. And thank you for the opportunity to present today. My talk will be devoted to the influence of residual stress and defect position on the very high cycle fatigue behavior of additive manufactured.
Sorry, Boris, I lost your presentation. Just a second, because could you share your screen? Because I can see it.
I think it's shared.
Okay,
can you see it now?
No, please. Could you stop the sharing and start again, because I touched the wrong button. Sorry, Boris.
Okay. Maybe now?
No. Just a second. Come cacchio ho fatto? Just a minute.
Yes, of course.
Grazie. Thank you. Okay, Boris, you can start.
Great. I hope you see my screen. Yes, let me please start from brief introduction. Today already have been talked a lot about fatigue, but I would like to start my talk about introduction to very high cycle fatigue. Of course, maybe most of you familiar with it. However, the main difference here is that the crack initiates not in the bulk, or not in the surface, on the surface of the material, but in the bulk. When and the very high cycle fatigue is a fatigue when the applied load is relatively low, but the number of the cycles is high. Yes, as I told, the crack initiates in the bulk usually from some internal defect. In case of the conventional materials, it's usually some non-melted oil, some usual non-metallic inclusions. But for additively manufactured materials, it can be any defect, process-induced defect, such as pore or lack of fusion. And the formation of the crack is accompanied by formation of a fine granular area, FGA, and which is surrounds internal defect. And this formation actually, I mean, the mechanism of the formation are, of course, somehow studied, but still there is no like single model which describes it, and it's still under study. And it brings us to the idea of the work. So first of all, that studying the very high cycle fatigue of additively manufactured materials is important, since it's already implemented in many industries, and the details potentially can work in harsh loading conditions, such as this high number of cycles. And it's important to study the very high cycle fatigue of these materials. But at the same time, additive manufacturing allows us to print small structures, like, for example, small artificial defects of desired size and a desired position. And such artificial defects can be implemented to the study of very high cycle fatigue. I mean, in general, to study this phenomena, and actually not only very high cycle fatigue, it can be useful for many cases. So in our work here, we study artificial defects and its effect on very high cycle fatigue. It brings us to the main part of the presentation. Like we used here powder bed fusion laser beam technology and printed with stainless steel powder. The parameters is shown on the screen, and also we used machines for fatigue testing. Actually, we did tests for conventional fatigue, but I will not show it here in this presentation. But here we will talk about ultrasonic fatigue testing for very high cycle fatigue testing. And just it worth to mention that it works on with 20 kilohertz frequency, and it all allows us to test 10 to the 10th power cycles for 6 days, while for general conventional fatigue machine, even with high frequency of 100 hertz, we need 3 years. So also it works also we use pulse-pause regime to get additional cooling during cycling, because due to resonance it can heat it, and also we cool our specimens with dry air system. And we used advanced material characterizations equipment like microscopy and also X-ray computer tomography. But the main, also one of the main is the machine which is for neutron diffraction stress measurements, which is equipped in Kurchatov Institute in Moscow, and we used for residual stress measurements, which allow us to measure residual stress in the bulk of the material. First of all, we wanted to understand what actually we can print, which artificial defect we can print with by our technology, our printers. And for that reason, we first printed such prism with many thorough artificial defects with different diameters. And we found that our artificial defects were surrounded by unwanted porosity. And we assumed that it's related to the contour parameters of the printer. And we started to optimize it to get the artificial defects to minimize this unwanted porosity. For that reason, we printed like 21 such prisms with different contour parameters and found the regime which allows us to decrease this unwanted porosity in the vicinity of the artificial defects. Then we checked the printability of these artificial defects, already not thorough defects, but like with limited size. And we compared it with the CAD model. We used like 3 different diameters and 6 heights. And to understand how the CAD relates with the reality. And it brings us to the testing. Actually, we insert these artificial defects in our very high cycle fatigue specimens. This is as built specimens, but we machined them before testing. So we inserted the artificial defects in the very center of the specimens, and we chose 3 sizes. And also we checked how it affects the microstructure, which we can see that artificial defects are surrounded by like fine grains. It's related due to different, first of all, different contour parameters, and also due to contact with the free surface and computer tomography results. Here, one interesting thing that despite that in many cases for optimization of our parameters, we got the smallest defect, which is like 90 microns in diameter. In some specimens for very high cycle fatigue, we couldn't observe them in computer tomography. So repeatability here may be not so good for the smallest defect. However, for the large, relatively large defects, like this one is 180 microns in diameter and 350 microns in diameter, they're quite good and correlates with CAD, as you can see it here. So this is a CAD red outline is a CAD model, and this is XCT results. It was to note that this is like 100 layers projected here, so the porosity is not so high as you can think. And also, we tested the specimens in a very high cycle fatigue regime, and after this testing, the specimen is not divided by two parts, so we can check the crack in the X-ray computed tomography, and we found that the cracks didn't start from the central artificial defect. And we also supported it by fractography. So despite that we have such large artificial defects in the very center of the specimens, the crack starts from some pores which are process-induced, I mean, additive manufacturing process-induced defects. And it was for all specimens. Also, I need to note here that in most cases, we had this formation of this fine granular area, as I talked in the beginning, which is typical for very high cycle fatigue. But it started not from the central artificial defect, but from process-induced defect closer to the surface. And this one is an interesting case. We didn't face with it before in the literature, that we have at the same time like 3 fine granular areas. So FGA, the 3 sites of the crack growth. For conventional materials, we didn't find that for additive, but for additive manufacturing probably not so. It's already like studied quite good, but still we didn't see such results. We related with the fact that additively manufactured materials just have much more defects in general, and that's why the probability of origination of the crack in different sizes is higher. And to sum up this central artificial defects work, we built this distribution. The gray bars relates to the process-induced defects in the specimen, and the blue is a critical defects which cause the crack initiation. So all of them here was process-induced artificial additively manufactured defects. And these process-induced defects, the critical was the largest one. I mean, as you can see here, but closer to the surface and not artificial ones. And we started to shift our artificial defects closer to the surface, and we tested like 5 positions here, and we chose only 2 sizes. And we started to achieve, to get the correct, started from the artificial defects when it's closer to the surface than previously. And you can see here like half a radius here, but still in some cases, like also the half a radius, we have this artificial defect here, but we have a crack initiation from closer to the surface. We relate it with the residual stresses. As I told, we measured it. So for machine specimens, residual stress is still comparably high. And the red line here is residual stresses. This is the center of the specimen, and this is the surface of the specimen. And we can see that the high compressive residual stress here and the tension here. And the blue line is probability of the crack initiation from the artificial defect versus distance from center. So we can see where we have the compressive residual stresses, we don't have any crack initiation from artificial defect. Then we shift it closer to the surface, to the tension zone, and we can achieve crack initiation from artificial defect. And also it was supported by our new results, which are for annealing. We annealed our specimens, so we stress relieve them, and we started to achieve this crack initiation from the central defects, as you can see here.
Boris, you have to. Okay.
Yes,
sorry,
actually, yes, I finished, and just a few words that residual stresses are important when we face with fatigue, and also its influence its behavior in very high cycle fatigue regime. So we need to control it, and I think that's it. Thank you very much for your attention.